All right, so we're going to look at 3269. 5 kilogram mass, so I'll call that MA, has a spring. A spring. So the spring constant K is 80 newtons per meter, attached to it moving at 6 meters per second. So VA is equal to 6. To the right, so that's going to be positive because I'm going to use my same standard Cartesian sign convention that up and to the right is positive. The end with the spring collides with a 10 kilogram mass, so MB is 10 kilograms and it's stationary, so VB is equal to 0. Determine the maximum compression of the spring. All right, so first of all, what is the maximum compression? So we want to find X. So you know, whenever we see a spring, there's two things that you're going to think of. You're going to think of either Hooke's law or the energy stored in the spring. Okay. So first, let's look at a picture of this. So I have A, and it has a spring on it, and it hits B, which is stationary. So now I want to know how much that's going to compress. So when it compresses, this is the hardest part. These two are coming together, and then when the spring compresses, they're going to be moving together. So before I do anything with that, I have to find what is this speed, V prime, that they're moving together with if the spring's being compressed. So I have MAVA plus MBVB is equal to MA plus MB times V prime. This is 0. And I want to solve for the velocity the two of them are moving together with. So I'm going to have MAVA divided by MA plus MB is equal to V prime. So 5 kilograms times 6 meters per second divided by 5 kilograms plus 10 kilograms. So it's 30 divided by 15, which is going to be 2 meters per second. And because it's positive, I know that means it's going to the right. All right, so now I'm going to do like I did in the last problem. And I'm going to look at my kinetic energy. I'm going to use conservation of energy to solve for that. So how am I going to do that? So first, initially, I'm going to do the kinetic energy of these. So I'm going to say 1/2 MAVA squared plus 1/2 MBVB squared is equal to 1/2 MA plus MB V prime squared, and then here's the key. We have the energy 1/2 kx squared, the potential energy in the spring. So we're solving for that x. So now let's get rid of this because that's 0. If we rearrange this, it's going to be messy, but I think we can do it. So we can say, and I don't think I'm going to do some fancy algebra. I'm going to say 1/2 MAVA squared minus 1/2 MA plus MB V prime squared divided by K. So if I have the 1/2 there, I have to multiply by 2. So now we're going to have 2. And then if this is squared, I'm going to take the square root. Ooh, there we go. All right. So now, well, 2 times 1/2 is 1. Same thing here. So now I can fancy it up a little. So I'm going to have mv a squared minus ma plus mb v prime squared over k. Oh, that doesn't look bad. So now, what are our numbers here? We have 5 times 6 squared minus 5 plus 10 times 2 squared divided by k, which is 80. So and then I have 4 times 15, 60. So 180 minus 60. Do that in my head. 180 minus 60 divided by 80. So 120 divided by 80 square root. So, and then square root comes out to be, it says 1.2247. So we'll just say 1.22 meters. So in this problem, first we use conservation of momentum, and then we use conservation of energy, and we get X.